Hi, my name is Miguel. Today I'm going to show how move constructors, a technique from C++, can be used to express a new class of types in Rust. This type of programming has frequently been cited as being incompatible with Rust's object model. I'm actually going to show that we can make it work. To get there, we're going to go on a journey through Rust, to C++, and then back to Rust again. This talk is a bit dense, so please make sure to ask questions in the chat if you get confused. I'm going to assume an intermediate to advanced level of familiarity with Rust throughout the talk. To understand why we care about move constructors, we need to understand self-referential types. We want to create a type that can point into itself. We'll start with a struct that contains a value x and a reference to x, which we're going to call putter to x. Very creative. If we write this code, Rust actually complains, because Rust requires us to give explicit lifetimes to any reference inside of a struct. Now, we don't actually want to add a lifetime to the struct itself. We want a lifetime that is sort of like a self-struct that refers to the lifetime of the struct that contains it. Unfortunately, Rust really doesn't have a way of expressing this, so we wind up having to use a raw pointer. The barrel checker just doesn't know how to deal with this today. I'm going to be using these little boxes containing fields and addresses in order to describe what pointers are doing at any given time. They'll become very important once we start tracking self-pointers into different structs. Now that we're using raw pointers, we can make cycle self-referential after constructing it on the stack by, assigning putter to x to a reference to cycle.x. This creates a little cycle inside of the pointer. So pay close attention to these arrows because they're going to change over time as we do different things with the struct. We can implement a get function that uses the self pointer to access the other field. Although a little bit contrived, this is a real thing in certain data structures. Being able to create self pointers is very useful for some classes of optimization and is pretty common in performance sensitive code. In order to get to work, we need to maintain an invariant in cycle. Putter to x must always be null, such as around initialization, or a pointer into itself and no other cycle. In other words, these are the only two shapes for a cycle that are allowed. In particular, we cannot have a cycle that points into another. This is not allowed and actually breaks assumptions that we want to make about this type. Now, it's pretty natural to want to factor out this initialization code into a constructor function. The only change from the previous code is that we've copied the letmut cycle part into a function and then called that function instead of using the cycle that we initialized previously. But if we do, Rust will move cycle as it returns out of cycle new. When we return by value, Rust does a move which changes the address of the returned value. But because putter to x is unchanged, it points into cycle new stack. It no longer points to x. Not only does this violate our invariant, but it makes get violate memory safety, because reading data from destroyed stack frame is not allowed. This is pretty bad, so it means that we can't write cycle new this way while maintaining the other properties we want. Because Rust moves are implemented as bitewise copies, cycle doesn't get a chance to fix up its invariant. This is a general problem with self-referential types. Their invariants break if Rust moves them, and Rust really likes to silently move things. However, Rust does provide a good way to avoid this pitfall. Pinned pointers. PinP wraps up a pointer type so that unsafe code, like our get function, can assume it never moves. Moreover, it stops safe code from accidentally moving its pointee. Safe code can still do whatever it wants without hurting unsafe assumptions. In general, this means that you can't get a mutable reference into the thing behind the pinned pointer. You can only get immutable references because you can't swap or replace out of those. Most Rust types are unpinned, meaning that they nonetheless can get moved out of a pin. Like, you can unpin an integer, because integers don't really know about their address. But a self-referential type like cycle is sensitive to its address, and therefore can't be unpin. You actually usually disable unpin by adding a special type that I'll show later. Most importantly, pin isn't magic. It's a library type, and it doesn't really change Rust's core semantics. You can still move things around as long as you have them by value. This is unlike types like slices and raw pointers, which introduce entirely new language semantics. This will be important later because we will add additional library guarantees that don't change Rust semantics at all. So let's go back to our dangerous implementation of cycle new, because due to this move, it immediately invalidates the raw pointer we create. If we use pin, we avoid this entirely. By returning a pinned box, we ensure that we can't move out of it at any time. It certainly doesn't move when we return out of it. We also need to make sure that it's pinned. The phantom pin type is a zero-size type that just disables unpin. Every type that cares about its address needs to include this type as a field. We can now write our code as before without any issues. Cycle.get will not dereference a dangling pointer. Note that we can't pull out of it like we could with a normal box. This ensures that safe code can't do anything rude. Pin lets us write unsafe code that requires certain values never move. There are a number of reasons you might want to do this. This comes up most commonly when writing asynchronous code in Rust, but there are other situations in which it's useful for, advanced data structures. It also enforces this in safe code. This means that safe code can't accidentally move stuff or do things that unsafe code doesn't expect. So unsafe code can do whatever it wants, and safe code can do whatever it wants, and unsafe code doesn't need to care. If you're watching closely, though, I actually needed to add a box to cycle new to allow me to return the pinned data. This is a problem. We need a pointer to pin in the first place. You can't pin an object and return it. That doesn't mean anything in the pin formalism. This leads to two major problems with pin. Number one, because stack pin data is going to be behind a mutable reference, you can't return it. It's the same as with any reference. Therefore, you need to pay the cost of an allocation and box it. We also can't pin data in collections. This is because basically every collection that can resize is going to move things when resizing. When a vec fills up, it copies everything and treats it as a move. When a hash map hits its capacity, it needs to do the same thing. Address-sensitive types don't really fit into the language, and using them widely is not free. Okay, so that's enough about languages that suck. Let's talk about C++. And no, this is not a C++ talk. I don't assume people have encountered it before, and I'm going to be very light on the weird C++ syntax. You can mostly treat it as Rust with a weird different syntax and no borrow checker. Let's recall our cycle invariant first. Remember that when we have a cycle, we want it to be null or a self-reference. We cannot have this version where it points to something else. Let's implement cycle in C++. First, let's define fields like we did in Rust. Next, we're going to need to be able to construct it. In C++, you use constructors to create values. Unlike a Rust constructor function that might be named new, C++ constructors get access to this, which is the C++ equivalent of self. It is as if cycle new somehow took a self parameter. We can take the address of this in the constructor, which we could not do in Rust. When we call the constructor, it silently passes the destination of the new object as the this pointer. So, as you can see, the version in the constructor, which didn't really know the concrete address, gets a concrete address when actually constructed. To make this work, C++ allocates space before calling the constructor. So this alloc byte array is just random untyped data. We then use the special new syntax, which is kind of like a raw constructor, to tell it, hey, please run this constructor with this explicit this pointer. Finally, we cast it to the correct type, and it's just business as usual as before. You can call functions on cycle, and it's perfectly normal value. In C++, all values get constructed in place. That is, space is allocated before the constructor runs. As a result, C++ values are always implicitly pinned. They always know their address. They're all address sensitive unless you say otherwise. So what would this raw constructor operator look like in Rust? On the left side, I have desugared the C++ constructors from before. On the right side, I have a transliteration of that into Rust. The raw constructor will be some kind of function call that accepts uninitialized data and constructs an object there, which is the same signature as the raw constructor. Although the raw constructor does take an additional argument, and we'll see how that mixes in later. Naturally, we want to capture this function signature into a trait, new. New is a constructor object that can create values of a specific type. But remember that we want to leverage the fact that constructors create pinned values, so we need to make sure to mark the Rust version of this as pinned. To implement a value, to implement a constructor, we create a new type. New cycle is a constructor for cycle. It takes an integer argument and sets up the invariant, like the C++ constructor. The difference between this and C++ constructors is that the additional type captures the constructor arguments. So instead of taking an integer, the new takes self, and self contains that integer argument. For other constructors, you might have more or less arguments. Note that it is not cycle that implements new, because there are many ways to construct a value. For example, you could imagine a default cycle type that takes no arguments. Notice that the body of the Rust constructor is almost word for word identical to the C++ version. New lets us capture the destination address and store it just like C++. We can now set up the cycle invariant without transiting through the null state. Again, just like in C++. It's almost as if we've ported the feature all bugs and all. The new trait represents constructor objects. You can build a constructor with some parameters and then run it on some storage somewhere. New:new is Rust's equivalent of the raw constructor syntax, and is intended to be wrapped in a more ergonomic API, much like how you usually don't need to call it in C++, and you can use the syntax sugar of declaring a variable instead. Even though we can now create cycles without an intermediate null cycle, we still haven't actually solved either of the problems we had. Now that cycle is pinned on construction, we can't return them at all. Maybe that's better, or maybe there's an abstraction we're missing. When a function returns, it needs a place to put the return value, and this is some place in memory called the return slot. C++ constructors actually get special treatment in the C++ version of this. When you return a C++ constructor, it's not as though you're assigning it to a variable and returning it. What actually happens is it constructs it in place in the return slot. This means that this code, which wouldn't work at all in Rust, works perfectly in C++ and dodges the move on return hazard. C++ implements this by adding a hidden out parameter to every function, the return slot. The this pointer used for the constructor is the return slot, unlike a local variable like it would be in Rust, or at least that's sort of how Rust behaves. That said, Rust does have a return slot, and it does use it a little bit in the C++ way, but it's not in a way that is accessible to users, and certainly not in a way that we can use it to run a constructor. So what if we just ignore the Rust return slot and build our own? Wouldn't that be better? That way we can control how things get placed into it. Let's represent the return slot with, sort of reference type that is data somewhere. It's uninitialized, we own it, and we're responsible for initializing it. It doesn't really matter where it is, but usually it'll be on a caller stack. Slots are the ideal location for running a constructor. They're raw memory waiting for a value to appear. We can define a method that accepts a constructor, runs it, and returns a reference to the result, consuming the slot. So in place, takes a slot from the uninitialized state, uses a constructor, and then takes the initialized state that the constructor results in. We can then fake a return slot by passing in a slot argument. Instead of returning by value, we run a constructor in the slot and return the resulting reference. This is actually very similar to the C++ arrangement under the hood, and while still leveraging the borrow checker. Both the slot and the pin share the same lifetime, so you don't have any of the concerns you would have in C++ where the slot might not outlive the result. Okay, so constructors plus slots actually gets us the first of these. We can genuinely return objects on the stack, even if it's not quite as ergonomic as it is for unpinned types. Progress. We still can't do the collections version of this, but C++ seems to make it work, even though all of its pointers are pinned. So how do they do it? Let's look at our C++ cycle type again. When we assign a variable to another, C++ actually makes a copy, rather than a move like in Rust. Much like clone, by default, this is a bitewise copy, which means we can run into the same problem where the self-pointer invariant is broken. Oops. In particular, remember, the bitewise copy means the pointer does not get updated. But like Rust, we can actually customize this copying behavior. The key difference is that while clone in Rust simply returns by value, C++ copies are done with a constructor. This gives us a chance to fix up the pointer to the new location before it's available for potential misuse. So the copy constructor looks almost identical to the normal constructor. It sets up the invariant and copies the data, copies X, but not the pointer. C++ variables don't move around like in Rust. You always construct new ones whenever you give a variable a new name. However, objects are always notified of when this happens, so you can fix up any invariance a byte-wise copy would otherwise break. This is similar to clone, but it has all of the power of constructors. Obviously, we need to port this to Rust because it's really cool. Again, let's write down the C++ code and see how we might write it in Rust. On the left side, we have a copy. On the right side, we have the Rust constructors exploded out into the version that manually calls the raw constructor operation. Unlike constructors, there's only one copy constructor for each type, so it makes sense to give it a specific trait, which we're going to call clone new. We don't need to add an additional type that represents the cloning operation. It's like intrinsic to the type being copied. The clone new trait looks almost exactly like clone, except that instead of returning by value, it takes a destination parameter, just like a constructor would. Implementing it is super easy. Like, we already know how to implement it in C++. We implement it exactly the same way in Rust. It's the same with the other constructor. Now, we implement this on clone because, as I mentioned before, being copy constructible is a property of the type, rather than them being very many distinct methods for doing so. In C++, you only really get one copy constructor, so it doesn't really make sense to try to generalize it in Rust. The new trait is a fusion of clone and new. It's the cloning constructor. But in Rust, we really like to avoid having to make copies because move semantics are awesome. So how can we recover them? Let's recall back to our move slot abstraction. When we create a value in a slot, because the slot is a unique reference to some memory somewhere, we're actually the sole owners. No one else will ever access the value even after the slot disappears. We can introduce a new type, MoveRef, which is like a mutable reference that captures this ownership property. Not all mutable references can be MoveRefs because some of those might be outlived by other mutable references or other types that are entitled to run the destructor. MoveRef has to be entitled to run the destructor. That's what ownership means. We can use MoveRef instead of mutable references for the return value of in place, since it produces a brand new value no one else will ever access. The key point is that MoveRef owns its pointee and not its storage. This means that we can move out of it, like box, but it's storage agnostic like a mutable reference. You can have MoveRefs that point to the stack or the heap. Now let's recall copy constructors. They're like a constructor, but instead of accepting some special constructor type, they accept a reference to self and write a copy of the supplied destination. We can define move constructors analogously by replacing the source with a pinned MoveRef. Pinned because that's what in place means. Unlike clone new, move new consumes the source, and that's why it takes a MoveRef. However, the implementation is almost identical, and it reveals the true nature of custom moves. They're just copies that consume the source. However, they can also mutate the source to disable its constructor or, properly move an owned resource. This is exactly what Rust's move semantics do. For vanilla types, that is, unpinned types, clone new and move new are just the usual clones and moves. There's nothing special about them, and it shows that this concept actually reduces to something we've already encountered in Rust. Move constructible types let us move the immovable. Despite being pinned, we can move data from one location to the other. This doesn't violate the pinning invariance because we control exactly how the value is moved, in a way that unsafe code can be made aware of. The trait is generic, so we can build custom collections that leverage it. Instead of doing a byte-wise copy to resize a vector, we can call the move constructor on each and every element as we're resizing it. This is how C++ collections, for example, resize when the contained value is not trivially copyable. Pin data in collection, so long as it can be move constructed, is totally something we can do. So yeah, we can actually do these things. We can make address-sensitive types feel as flexible as normal Rust types. We can return them, we can put them in collections, we can really allocate them wherever we want, and we can specify complex moving strategies that the normal Rust object model would not let us. That said, we need to muck around with uninitialized data in order to use any of this, and the ergonomics are really bad. Most people are not going to be writing unsafe code. They're going to be using these types and the unsafe code under the hood, but it would be best if they don't have to do any of that manually. So And placing a constructor actually only really cares about the constructor value you use. Everything around it is boilerplate that can be inferred. However, recall, returning pinned data is impossible, so we can't use a function to do this, but we can use macros to work around it. For example, the slot macro could be used to allocate some space on the stack and then immediately stick it into a slot so that it can only be accessed through the slot. Unfortunately, the slot macro can't even be an expression since it needs to allocate on the stack. We can use the in place operation defined on slots previously to construct values. Unlike the example above, this produces a MoveRef. We can add convenience functions to slot that make it easy to call the clone and move constructors as well. So now we don't need to deal with any unsafe code in order to call constructors. We can just call this macro, allocate some space, and then put it directly inside them. This is a common enough pattern that we can add a macro to do this even more concisely. The choice of syntax isn't really important. Ultimately, we can make constructors feel simpler and easier to use. We could also potentially add functions that let us place macros into boxes, into arcs, and other similar things that you would want to do with a regular value. Really, it's a matter of what conveniences you want to add. Although constructors are implemented purely as a library, we can use macros to add custom syntax to use them safely. Ultimately, what they look like is up to the constructor library. This only scratches the surface of how macros can make constructors feel more natural and part of the language. There is still a lot to do in this topic. I already implemented the core traits in a crate. Check out move it on crates.io. I want to actually build a move respecting vec and hash map like I described earlier. C++ has already implemented such things, so it's just a matter of porting the analogous thing from a C++ standard library. I'm most of the way there with vec. I don't know to what degree I want to attempt hash map until someone really needs it, because hash maps are pretty complicated. This concept is also very useful for mixed Rust C++ code, but I think it can also be useful for certain kinds of pure Rust as well. I'd like to make examples of both more readily available to motivate this kind of API more. In the process of developing this, I sort of realized that pins docs don't express all of the things you can do with it. It only expresses a certain subset of it. I'd like to improve the documents so that they more clearly state the guarantees and what they mean for API design. I have a working version that I'm hoping to propose to the Rust standard library at some point. Finally, there are tons of C++ features that can make working with constructors easier, such as syntax trigger from being able to have struct literals, using constructor operations as an expression rather than as a binding. There is a very long list of these things that I'd like to port someday in order to make constructors easier to use. Now, none of this would have been possible without the help of many people who I've discussed this feature with, who suggested ways to make it more concise, who pointed out flaws in the original design. However, I want to especially thank Tyler Mandry. After he corrected something I asserted about pin, I realized that the pin guarantees could be used to express constructors. I'd also like to thank Manish Gorgokar, who encouraged me to publish this idea widely for the benefit of both Rust C++ interop and the development of Rust in general. Thanks for listening, and I hope you enjoyed my talk.